Well, let me just repeat that Professor Claessen is a world-leading expert in electron and X-ray spectroscopy, especially with synchrotron radiation, which will be the topic of his presentation, of his lecture today. But before he starts, let me also say that during the lecture, you may use the chat to ask questions. If there's time at the end of the lecture, I will forward these questions to Ralf Claessen. And otherwise, there will be ample time after his second lecture tomorrow that you can ask these questions then in person. Ralf, please.
Yes, thank you very much, Jochen. Everyone can hear me? Yeah, thank you very much for the kind introduction, and thank you also to Mark and the other organizers for having me on board. I'm very happy to be part of this Les Houches summer school. I would have been even more happy if we would have been able to gather there in person, and this would be the picture that we would be involved in, but this was not to happen. So everyone of us is sitting at home or in their offices. Some of you are probably sitting on their couch and watching me. And I am personally sitting in Würzburg, which is this place here in the middle of Germany. Many of you may have heard the name or may not even have heard the name. It's a small university place about an hour driving east of Frankfurt. And as you're all physicists or maybe material scientists, it's actually a place that you should be knowing because that's the place where exactly 125 years ago, the X-rays have been discovered. And that's very matching because X-rays are important for the topic that we will be talking about today. As I said, this was discovered in 1895, November 8th, can be very concretely be fixed when this happened. As you can imagine, we had planned a lot of activities for this year in Würzburg to commemorate this anniversary. Again, all these events had to be deferred or canceled. But if you want to know more about what's going on and a little bit more about the historical events, then you can find this on this webpage that is listed here. Okay. This brings me to today's and tomorrow's topics. I have split my lectures into two parts. One where I will give you a pedagogical introduction to the methodology of photoemission spectroscopy, and then in the second part I will discuss a number of applications to transition metal oxides, in particular to systems with electronically active interfaces. This would naturally be distributed between today and tomorrow, but depending on time, I may already start with part 2 today. Okay, let's then first motivate us why I will concentrate on transition metal oxides in particular. I guess with the auditorium that I have, I don't have to go into much details. The fascinating thing about 3D transition metal compounds is that the open 3D shell or the electrons in the open 3D shell behave very diverse. They can act as delocalized particles giving rise to metallicity, but because the 3D shell is atomic-like, they can also behave as local charges with local magnetic moments, for example, and that's why we have a lot of different quantum phenomena and quantum states in these materials. We have magnetism, we have the coupling to the lattice degrees of freedom, we have orbital degrees of freedom, and they can all match together and give rise to all kinds of multiferroic behaviors, superconductivity, colossal magnetoresistance, and all that more. Now, that's already fascinating if you look at the bulk materials, but owing to the great progress that we have been, or that the community has been having over the past 1 or 2 decades in synthesizing these materials in the form of ultra-thin films and even heterostructures, we have been able to grow these materials in all kinds of complex compositions that you don't find easily in nature. So these are artificial compounds, if you will. And this allows us to control a lot of these properties that we have in these materials and turn them into actual functionalities that may be useful for applications. We can apply strain, we can dope the materials by electrostatic means, by building field effect transistor-like structures. We can induce magnetism in otherwise non-magnetic materials, or use superconductivity proximity effects, and so forth. Now, a lot of this physics is going on at the interfaces of two different oxides. And in order to understand what's going on, we need access to the microscopic electronic structure and microscopic degrees of freedom. And that's where photoelectron spectroscopy comes into play. It can provide us in principle with a lot of information about, starting with chemical composition, about the detailed electronic structure, and we can actually try to resolve the vertical profile of electronic and chemical properties through such an interface. Okay, then let's go right into the topic. And I have divided my talk in little chapters, and I will always have a little title here. And I will first talk a little bit about the history of it. In this case, we will be discussing photoelectric effect per se, as it was discovered in the end of the 19th century, where experimentalists such as Heinrich Hertz or Wilhelm Hallwachs have found that if you expose a metal with ultraviolet light, electrons get emitted. This effect was known for quite a while. That's the photoelectric effect. But it was actually Albert Einstein who gave the correct interpretation, namely that the light that impinges on our photocathode has to be thought of as a stream of light particles, of photons, which each of them carry a certain energy package. And as it interacts with an electron in the solid, this energy is transferred to this electron, and if the energy is high enough, and that's why we need short wavelength light or high energy photons, the electron will be able to leave the solid if it overcomes the work function. So so this gives rise to this famous formula that the energy of the electron is proportional to the photon energy, or the proportional to the frequency of the light, minus the work function that has to be overcome. This equation actually applies not to all electrons. This is the equation for the fastest electrons. And as soon as you have enough photon energy here to release these electrons, you will detect a photo current coming out of the sample. But of course, it's not the very fast electrons that get detected. You have also electrons which will be a little slower. And the first one who really turned this into a useful tool was Kai Siegbahn in the 1960s, where he utilized or turned this into a spectroscopy by detecting or measuring the photoelectron energy distribution. And by assuming that you have energy conservation in this photoexcitation process, you can then get information about the original binding energies of the electrons in the solid. This goes by the name of electron spectroscopy for chemical analysis, because this was applied mostly at the time to core levels of materials, and the core level energies, the binding energies of the electrons in the core levels, is element specific, and therefore the energy distribution of the photoelectrons gives you information about the chemical composition of the sample. This, by the way, was also awarded with a Nobel Prize in the early 1980s. This is the principal picture that we have to keep in mind, and for that we start out with the electron energy distribution of the electrons in our solid. And we have to distinguish between two types of electrons. We have those electrons that are sitting at in the core levels, which are tightly bound to the nucleus of the atoms. And these binding energies are, as I said before, element specific. And then you have the valence electrons that sit close to the Fermi energy. Here I have plotted a metallic situation where we have valence electrons here sitting all the way up to the Fermi energy. These electrons are no longer locally bound. They are spread out in the solid as Bloch waves. And this gives rise to a density of states. And then as you excite these electrons with a given photon energy, you can excite them across the vacuum level. The distance between the vacuum level and the Fermi level, to which we refer our binding energies, is just the work function. And then you will see that the energy distribution of the photoelectrons will simply reflect the energy distribution of the electrons prior to the excitation. Of course, you can only excite electrons that have been occupied states before, and that's why you see from the density of states here at the Fermi level only the occupied part. There will be, of course, also an unoccupied density of states, but because there are no electrons sitting there, that's not accessible by photoelectron, by photoemission. Okay, this is what this looks like if you look on a large energy scale. This is an example. It's an XPS X-ray excited photoelectron spectrum from magnetite, which is an iron oxide. And in your spectrum, this is the current or the intensity of the photoelectrons versus the binding energy. In the actual experiment, you first measure them as, of course, as a function of kinetic energy, but then you can transfer this energy scale into a binding energy scale. And you see these characteristic peaks here in these in the spectrum, and these can be identified as simply the core electrons. So here we have the iron 3p core level. This is the spin orbit split iron 2p core level, iron 2s. Here, this very sharp line at about 530 electron volt binding energy is just the oxygen 1s core level. And very often you have some additional features in there which are assigned here. These are Auger electrons. When you excite electrons from the core levels, you create core level holes. And these holes can decay again by Auger processes. So electrons from higher occupied core levels can fill this core hole. Energy gets released by that and can be absorbed by other core electrons, which will then be excited into the vacuum. So these are not photoelectrons, these are Auger electrons, but they are part of the spectrum that you measure. A second feature that I would want to point out here, and we will address this a little later, is that as you go to higher and higher binding energy, you see that we have a kind of a smooth, unstructured background that is increasing monotonically as you go to higher binding energies or lower kinetic energies of the photoelectrons. And these are due to secondary electrons that are generated by collision processes, inelastic collision processes that occur when photoelectrons transfer from their locus of excitation to the surface before they actually are released into the vacuum. So this is electron spectroscopy for chemical analysis, because that gives you chemical information. There is even more chemical information than just encoded in the binding energy. You can also say something about the local binding environment of your transition metal. And here I have shown you the iron 2p range. This is this part here, blown up to a finer energy scale for various iron oxides. And the bottom curve you see here, iron metal. That's just plain metallic iron. And then here we have three different oxides. The degree of oxidation increases from bottom to top. This is iron monoxide. On the top we have iron sesqui oxide, iron 203. And in the middle we have magnetite, Fe3O4. What changes as you go from the metal to these stronger and stronger oxidized oxides is the valency of the iron ion in the compound. In the metal we have neutral iron atoms. In iron oxide, we have basically iron 2+. In the sesqui oxide, we have iron 3+, and magnetite happens to be a material where iron can absorb two different valencies, 2+ and 3+. And as you can see here, the binding energy, the actual binding energy, the precise number of the binding energy increases as the valency increases. And also, you see that the line shape changes a little bit. And this is related to two things. First of all, the increase in binding energy is due to the fact that as the valency increases, we have less 3D electrons in the valence shell. And because the 3D electrons are not only sitting a certain distance away from the nucleus, but also have a finite probability to stay around the nucleus of the atom, this charge is lost and can no longer screen the nucleus. So for a 2p electron that is measured here, the nucleus seems to become stronger and stronger positively charged because we lack more and more 3D screening charge, and that's why the binding energy appears to be higher. And the second effect is that we don't just have non-interacting electrons. The 2p electrons interact with the 3D electrons by Coulomb interaction. Turns out if you look at the radial distribution of the wave functions, the 2p's and the 3Ds have some spatial overlap, and so there is some Coulomb interaction going on, so that we get multiplet effects between the partially occupied 3D shell and the 2p shell in which we now have created a core hole. And this gives rise to multiplet effects, and these are reflected in these line shapes. So as you change the filling of the 3D shell by going to higher and higher valency, you see characteristic changes in this multiplet structure. There are additional effects, shake-off or shake-up effects. For example, when you take out the 2p electron, you create a core hole, which can be thought of as a positive background charge. And then the system can minimize energy by transferring an electron from a ligand. In this case, it would be an oxygen 2p electron that gets transferred from the oxygen 2p to the iron 3D shell, to the valence shell, in order to screen the nucleus. And this transfer costs a little bit of energy, and that can be seen here as a satellite. Here, for example, this is the charge transfer satellite that you see typically for divalent iron. For trivalent iron, as here in iron 203, it has a different energy relative to the main peak. And so these characteristic charge transfer satellites can be taken as fingerprints of the actual valency. In fact, here in magnetite, which is of mixed valent nature, the spectrum that we see is simply a superposition of the divalent and the trivalent spectrum that we see in the FeO and Fe2O3. So that's something you can also utilize in order to extract chemical information from your core level spectrum. And then, of course, we have the valence electrons, and that's particularly important because these are the electrons that are responsible for all the interesting materials properties, conductivity, optical properties, and so forth. And you can, of course, also look at them directly. Here I show you an example of titanium oxychloride, which is a low-dimensional, quasi-two-dimensional MOT insulator. And in this case, it's taken with XPS, which means we take X-rays as excitation source radiation, and a second spectrum that has been measured with ultraviolet light with photoelectrons of 21.2 electron volts. But both of these spectra are measured with just detecting the energy distribution of the electrons. We do not measure yet any angle distribution. So we do not look at any K-space resolution here. So in this case, we measure basically the density of states. And as you can see, we have two major structures here in the spectrum. We have these electrons sitting here, which turn out to be the titanium 3D electrons. In fact, it's just one 3D electron per titanium ion in this compound. And we have, which is a typical signature here of oxides, we have this very strong oxygen 2p, and in this case there's also some chlorine 3p contribution here on the main valence band. As you can already see here from these two different spectra taken at different photon energies, there are some changes here. And these changes are due to matrix elements, or the transition probability for exciting an electron from the solid depends on A, the photon energy, and B, the orbital nature of the electrons that we excite. And so there are some certain variations in here. So you have always to be a little bit careful when you interpret such data. It's not the bare density of states, but it's weighted with the relative excitation cross sections. But overall, as you can see by the comparison here to a density functional type calculation, the agreement is quite good. Okay, so that's in a nutshell the most important message. What we can measure with photoelectron spectroscopy is chemical and electronic information. From the chemistry, we can learn about the elemental composition. We can learn about the precise chemical bonding and the valencies of the atoms in our compound. And concerning electronic structure, that is the information about the valence band, we can measure the density of states. But we can also, as we will see a little later, measure momentum information. So we can really map out the band structure, look at the shape of the Fermi surfaces, and that becomes also very important for transition metal oxides. We can measure the spectral function. All the pictures that I have been using so far depend on a picture of electrons being independent of each other in the solid. So it's a single electron picture, if you will. But in reality, electrons will interact, and that's particularly strong effect in 3D shells. And so we have to think about it as a many-body excitation. And you can then map this onto the concept of a single particle excitation spectrum or spectral function, which for the theory theorists among you, that is simply the imaginary part of the single particle Green's function. But I will get to this in a few minutes. And before we go to discuss the theory behind photoemission, let me say a few words on instrumentation, because that's the part that absorbs most of our time and resources. And what you need for photoemission are basically three ingredients. We need a photon source to excite the photoelectrons. We need a detector that allows us to measure the kinetic energy of the photoelectrons, an electron energy analyzer. And as you will see, we will need ultra-high vacuum to allow this process to happen and to maintain conditions which allow us to probe the electronic structure of the solid under investigation. Let's start with the photon source. You need something that produces photon energies high enough to overcome the work function. Typical work function for a solid is somewhere between 3 and 6 electron volts. So you want to have photons that have 5 electron volts or more in order to excite photoelectrons. And one particular important source that we use in the laboratories is a helium lamp. So we need photons of the order of 20 to 40 electron volts, typically, in order to map out valence bands and band structures. And that's called vacuum ultraviolet radiation. Vacuum because this energy range can only be transmitted in vacuum. Any gas would absorb this radiation right away. And the most easy way to create such radiation is by exciting helium, a helium gas, either by electron bombardment or by microwave excitation, or by just applying a high electrical field. And then you can excite a 1s electron into a 2p state in helium, and then this state will relax again and emit at a frequency at about 21.2 electron volts. This is done with a helium rare gas discharge lamp, as is shown here. Now it turns out the spectrum of this lamp is a little bit more complex. It does not just have a single line. The line that we are using mostly is this one here, helium-1 at 584 angstroms wavelength, or 21 eV photon energy. But there's a little bit more of light coming out. You have some low energy satellites sitting at higher photon energies, or you have here helium-2 radiation, which comes from excited helium ions in the gas. You can either try to monochromatize your light by using a monochromator, which always costs you a little bit of intensity and also a lot of money to implement this, or you just live with these satellite structures in your spectra. And sometimes you see this when you look at published photoemission spectra, that you have an echo or a second image of your spectrum shifted by a certain photon energy, and that comes from these satellites here. But once you are aware of their existence, it's easy to identify them. The energy here is not high enough to excite core levels typically, and so you have to go to to a source that produces X-rays, and that you do with a conventional X-ray tube, except that you have to do this in vacuum, because as we will see later, everything has to be done in vacuum here, but that's not a principal difficulty. And one excitation line that is used here very frequently is aluminum K alpha radiation. So you use aluminum as an X-ray anode, and the photon energy here is 1486 electron volts. Now these two sources deliver basically just one kind of one photon energy or one wavelength. Very often you want to be able to tune your radiation and to go to different photon energies in order to go to a position, to an energy where the cross sections for a particular core level or particular valence state is a valence electron is high enough or higher than for others, so that you can single them out. And for that you need a tunable source of either VUV radiation or X-ray radiation. Now it turns out that this is not easily achievable in the laboratory, and then you have to go to these kind of light sources, which are a little bit larger, namely to a synchrotron radiation source. This is basically a large electron accelerator in a circular form. Here I have shown you several aerial photos of such synchrotron sources to give you a feel of how their magnitude. This is the Swiss light source in Willigen, Switzerland, the Diamond light source near Oxford, and Soleil near Paris. But you have to be aware, not every big round building is a synchrotron. Here's another big round building, which would be ideal to host a synchrotron, but that's just the headquarters of Apple in Cupertino. So that's not a synchrotron source. So what happens in there? As I said, it's basically a big accelerator. Actually, it is a big storage ring. So what you do is you take an electron source, you produce electrons, you excite them with a linear accelerator to energies where they propagate with nearly the velocity of light, and then you feed them into a storage ring. It's what, as the name says, it's just a ring in which your electrons are stored, and in order to keep them on a ring, you have to radially bend the electron beam here. You do this by bending magnets, by magnetic fields. You just use the Lorentz force to keep them on a circular path. But as soon as you accelerate an electronic charge, it will emit radiation. And that happens in these bending magnets here. So when you try to keep them on the circular path, or here in this principal picture, whenever you bend the electron path, there is a fan of radiation coming out here. This had been done in the early days as parasitic use. These accelerators had been used by the high energy physicists and people that wanted to use radiation. Just were using it here as parasitic users. The generation of the light is actually to the high energy types is a nuisance, because it means that the electrons in the storage ring lose energy, and that's what they want to avoid. But for a user of the radiation, of course, that's exactly the reason why you want to use this here. You can actually increase the amount of intensity coming out of such a magnetic field device by engineering this in a certain way. For example, if you not use a homogeneous magnetic field here, but an alternating field by putting here magnetic pole pairs in reverse and alternating orientation, you can wiggle the electron beam here. I don't know if you can see this very well. And that produces you a much finer focused and much more intense beam. In fact, you can, and if you apply very high magnetic fields here, and you adjust the field strength by the distance of these pole pair shoes, that's the so-called gap. You get an undulator where this light is coherently excited. And these are also the structures they are used here in synchrotron facilities, but they are also used in particular in the new free electron laser facilities that we have at some places in the world. Now, why would we do this? What is the big advantage of this radiation? Well, first of all, you have a very wide, continuous, tunable energy range. You can, in such a storage ring, induce photons from the infrared to the very hard X-ray regime here, from 0.01 electron volts from millivolts, that's infrared, to gamma rays of the order of 100 kilo electron volts. So this is a huge range, and by suitable monochromators, you pick out the photon energy range that you want to use. The radiation coming out is strongly bundled. It's a very intense beam. For example, if you use a laboratory X-ray tube, the radiation is not focused at all. It's not bundled at all. It's just going into 2 pi half space. And so when you have a certain sample which has a given size, you lose a lot of photons which never hit your sample. But with the synchrotron beam, you can be much more intense. The light coming out of the ring is polarized, so you can use also the polarization to do certain experiments. It can be linearly polarized, but it can also be circularly polarized. That's, for example, important if you want to do XMCD, X-ray magnetocircular dichroism. And the light coming out is structured in time, because you don't have a continuous electron beam here in your storage ring, but you have a sequence of electron bunches, electron packets that run around here that are equally spaced in distance, and so you get a certain time structure in your beam, and that you can use also for time-dependent experiments. So it's a very versatile, very intense light source, but of course it's also a complex light source. You cannot realize this in your laboratory, so you have to go to these big places and apply for beam time. And all the big facilities, they cannot be beaten in terms of photons per second. But if it comes to systematic experiments, the lab sometimes has an advantage, because you have more photons per year than you can ever achieve at a synchrotron light source, because the beam times are, of course, only a finite length. Okay, so for the light, now we need to detect the electrons. And we have to measure the photon energy, and you do this with an electron energy analyzer. And what we use here it typically is a hemispherical analyzer. So that's basically, you can think of it as a capacitor that depends on an inner sphere and an outer sphere. and you apply a certain voltage between them, and you create by that an electrical field. That's basically a Coulomb field. It's an 1/r field in there, and all electrons that get into this field will propagate on Kepler ellipses. Now, when you get the photoelectrons from your sample, you focus them onto an entrance slit. So you have a little slit here before the electrons enter this concentric hemispherical analyzer. Enter here, so you have if you will, a point source, but the electrons will have different energies. And depending on their energy, they will either go on a path that will bring them to the exact opposite position on the other side of the hemisphere, if they have traveled by angle pi, 180 degrees. And if they do that, they are exactly on the so-called pass energy. Electrons that are lower than that in energy, they will be attracted here by the positively charged inner hemisphere and will reach a position here which is away from an exit slit. So you can think of it just as in an optical spectrometer. And electrons that are too fast will not be bent as strongly as the electrons that have the pass energy, and they will hit here this wall and will also not hit the exit slit. And by this, you filter out a defined energy, and then you can measure the amount of photoelectrons at this energy. And in order to measure other energies, you decelerate the electron beam hitting the entrance slit, or you accelerate them, and by that you can scan the entire energy range. This was the way such analyzers have been used up to about the mid-90s or so. And then the community has made a big step forward by utilizing the progress in detector technology that comes mostly from the people working in the field of X-ray diffraction. And they had developed a series or different types of two-dimensional detectors, position-sensitive detectors. And that allowed us to replace the exit slit by this 2D detector, because now we do not just measure the energy of the electrons hitting the exit path, we can measure all photoelectrons with different energies simultaneously, and that of course gives rise to a much faster measurement. What we use here as 2D detector is basically a microchannel plate. So these are very thin glass plates with millions of little holes in them, which act as electron multipliers. You apply a high voltage at them, so they will turn a single photoelectron hitting the entrance side into an electron cloud of 10 to the 6 to 10 to the 8 electrons. And these electrons will then be further accelerated onto a fluorescence screen and be turned into a photon flash, which will be recorded with a CCD camera. That's a typical detector that we have in these analyzers. Now, the energy, as I said, is encoded in this position here, in this linear deviation of the different paths that the electron travel in our analyzer. But as I have a two-dimensional detector, I can also use the other direction, and that can be used to measure the angle with which the electron have originally escaped from the solid. Here you see three beams, green, yellow, and red, that have different escape angles. They are imaged onto the entrance slit, come here into the analyzer, and now let's assume that they all have the same kinetic energy to hit the middle line of our detector. So they will be recorded as having this particular energy. If they had a higher energy, they would have detected further out here, and if they had a lower energy, they would have been detected here. So this axis is our energy axis, but you can see that different escape angles are now imaged onto different positions in this direction here. So this direction encodes the angle with which the electrons have come out of the sample. And that is nothing else than the momentum information that we can record from our electrons. And that allows you then to simultaneously measure angle and momentum and map out a Fermi, a band structure, for example. So this would be, this is energy, this is momentum, and then you see that you have certain energy versus momentum dispersions and bands. This is the same set of data now shown as actual spectra measured at different momenta. Again, the horizontal line is the binding energy axis, and the vertical now is the intensity. But as I stick here spectra taken at different momenta. This is how we can map out a band structure. Okay, and finally, vacuum. Why is vacuum so important here? And that is related to a property that I haven't addressed before. You excite electrons typically somewhere within your sample, but you want to detect them in the vacuum, so they have to come out of your sample. So they have to travel towards the surface. And on the way towards the surface, they will undergo inelastic collisions with other electrons and create interband transitions or plasmon excitations of the electrons in my solid. By that, these electrons, the photoelectron will lose energy and forget about the original energy information that I wanted to measure. And there's only a certain fraction of photoelectrons that ever reach the surface without having undergone such an inelastic decay, or an inelastic collision. And it turns out that the probability with which such a photoelectron can interact with the other electrons, it depends on the energy, or you can turn this into a mean-free path. The distance an electron, the photoelectron, can travel without undergoing such a transition. That's called a mean-free electron path. And just to give you a feel what this means in practical terms, 95% of the signal that you get out of the sample of the direct photoelectrons that still carry the original energy information come from a depth of 3 times this mean-free path from the surface. Now this turns out to be a number relatively independent of the actual material you're looking at, and that's why this is called the universal curve. This gives you here the mean-free path of photoelectrons as function of the photoelectron kinetic energy. And that, of course, scales a little bit with the photon energy. The higher the photon energy, the faster also the electrons. And you can see that in the energy range that we have been discussing so far, so I was talking about photon energies of 20 to roughly 2000 electron volts. You are in this energy range here. That the mean-free path of the photoelectrons is rather low. It's only of the order of a few tenths or even less than 10 angstroms. These are atomic distances, and that means that for the energies that I just addressed, the photon energies and the resulting photoelectron energies, we only probe a relatively thin layer of just a few atoms thick or a few unit cells thick. So these are the numbers, and that means that photoemission, at least in this conventional way with the photon energies just mentioned, is a rather surface sensitive method. And that will, as we will see later on, be very important if you look at transition metal oxides. But I wanted to argue why we need a vacuum. And the point is the following. If you have a material with the surface, and that's shown here, you have a bulk, a volume, that defines the crystalline properties of your material. At the surface, the atoms may be a little bit relaxed or show some surface reconstructions. And then typically, if you take a material at ambient conditions, ambient atmosphere, it will be covered with adsorbents. There will be water on your surface. It may be oxidized. You may have some CO2 molecules sitting on there. Somebody may have touched on the surface, and you may have some organic compounds out there. And so typically you have a situation like this. Now you have to remove this. Remember that the mean free path of the photoelectrons is just a few angstroms. And if you start out with a surface like this, which is contaminated, and you try to excite photoelectrons, most of your photoelectrons will come from this adsorbent layer and not from your actual sample that you want to study. So what you measure would be the dirt, but not the sample itself. So you have to remove this dirt first. By some means, you can either cleave your crystal, or you can try to clean it by ion bombardment with argon ions and subsequent annealing, or you can just anneal and hope to release to clean your surface by just thermal treatment, and that's then what you should be looking at. But the lifetime of such a clean surface is not particularly large, especially not if you do this at normal conditions. So first of all, we have to keep in mind that even a clean surface may be different from the volume. What we want to study is mostly this volume, but even if I have a clean surface, there may be some changes. For example, here I have some surface relaxation that would affect the band structure, for example. And the clean surface that I have just prepared does not necessarily stay clean. And you can do a simple kinematic estimate how long it takes as function of pressure to keep the surface clean. When we have a material, it will always the surface will always be the interface to the vacuum, and what we call vacuum is not really a vacuum. It's not empty. There will be a certain density of gas. It may be a low density, but it is nonetheless a density of residual gas atoms and molecules, and they can eventually, when they hit the surface, stick to the surface and then give rise to the growth of such an adsorbent layer that I just depicted previously. And then you can look at the time scales, and if you do this, if you do a simple kinematic estimate, you find that at ambient conditions, 1 atmosphere, the typical lifetime before you have one monolayer sitting on your surface is just on the order of nanoseconds. If you go to lower pressures, you find that you increase the lifetime, but even at 10⁻³ millibars, which is already quite a good vacuum, you find it very difficult to breathe in this atmosphere. The lifetime is still on the order of milliseconds. So that's nothing, not a time scale on which you can do an experiment. You really have to go down to very, very low pressures of the order of 10⁻⁹, better even 10⁻⁻10 or 10⁻⁻11 millibars to get lifetimes which allow you to do a meaningful experiment. For example, here in this simple estimate, you find that at 10⁻⁹ millibar, we have a lifetime of 1 or 2 hours. That's a typical lifetime, and very often, depending on the chemical reactivity of your surface, you have to still be quick to do these experiments here before you get oxygen atoms, for example, to change your surface. Okay, that's why we need ultra-high vacuum, and that's why you always see this huge amount of stainless steel in our laboratories, because we have to do everything under these conditions. You have to prepare your sample under these conditions, and if you have to prepare them in a, for example, MBE or pulse laser deposition setup, you have to move your sample to the actual photoelectron spectrometer under ultra-high vacuum, which you can do, for example, with such magnetic transfer rods, but everything has to be done under UHV, and that makes the technique so expensive and difficult to handle. Okay, so that's instrumentation. That's all the dirty work that you, at least the theories among you, never see, but that's what keeps most of our times and resources. But let's go to the more fun part, namely to the theoretical picture of photoelectron spectroscopy. How do we get from the energy distribution of the photoelectrons to the actual electronic structure that we are interested in? And in a most simple picture, we can think of this as a situation where we start out with an half-infinite solid with a surface. The surface is here at z = 0. This is our solid, and this is an energy axis. And here we have electrons sitting in some core level states or some Bloch states in in our solid. We have to excite them in energy to a state that lies well above the vacuum level. And then the electrons can come out of the of our solid here. They have to penetrate the surface, and then in the vacuum they will propagate as free electron waves until they finally hit our detector, where they get analyzed in energy and finally create a signal that we can count. You see that I have drawn this here with an amplitude that decays towards the interior. When I mentioned before that when electrons travel from the excitation site somewhere in the interior of our sample, it has to propagate to the surface and then may lose energy by inelastic collisions. And if I plot this as a wave function here that gives you measures the probability with which I can detect an electron coming from the interior of my sample, I have to take this into account, and there will be a high probability to count electrons coming from immediately excited at the surface, and an electron that has been excited towards the interior has less probability to ever reach my detector, and that's why this wave function seems to decay exponentially into our solid. We call this kind of state, well, let's start with the initial state. We have an initial state from which we excite. That's just the normal Bloch wave that we have in our solid, characterized by its initial state energy and its wave vector Ki. And then we excite this into the state here that I've drawn up here. And we call these final states time inverted lead states, because they are really the time reversal version of the states that you create when you do a lead experiment, a low electron energy diffraction experiment, where you shoot an electron beam at the surface and then look at the reflection, and part of it will transmit into the interior, and now we reverse this in time. In vacuum, these waves are just free electron waves, which have a certain momentum, Kf, which may or may not be different from the initial state momentum. And then we have to match it to the high-lying Bloch states that we have in our solid, and also have to take into account this damping due to the electron-electron scattering appearing here in the solid. And what we measure then is this final state energy and the wave vector of our photoelectrons. So this has to be viewed as one single coherent process, but that's on a theoretical side not easily handled, and therefore what people have come up with is a simplified scheme in which you break this down in 3 independent steps. And that's called the 3-step model. You start out with an excitation deep in the volume between Bloch states, initial state Bloch state and the final state Bloch state. Then you treat the propagation of the photoelectron towards the surface, and then you take into account what happens at the transition from the volume, from the crystal into the vacuum. And that's what we will be looking at now. This 3-step model, and let's start with the first step. This is shown here. That's an easy one because we do not know anything about the surface yet. We describe the transition from the initial state to the final state, and we do this by Fermi's golden rule. This is just time-dependent perturbation theory. We have the Hamiltonian that describes our crystal, our electrons in the crystal, which gives us the Bloch states as the eigenstates of our unperturbed Hamiltonian. And then we add our photon field as a small perturbation, time-dependent perturbation. It's an oscillatory electrical field with frequency omega. And then Fermi's golden rule tells us that we have a certain transition rate from the initial state to the final state, which is basically given by this matrix element. Squared, where you go from the initial state to the final state via this transition operator, and that's basically the vector potential multiplied with the momentum operator A dot P. This is basically at the end will be the conventional dipole approximation. And you have energy conservation here. You have this delta function, which ensures that if you start with the initial state energy of electrons and you add the photon energy, you end up at the final state energy at which the photoelectrons get detected. When you analyze this photoexcitation cross-section or this matrix element in more detail, you will see that we have momentum conservation, namely that the final state momentum is identical to the initial state momentum, as long as we are on the dipole approximation. If modulo a reciprocal lattice vector, so we may have such a vertical transition, or we may have a transition into the next Brion zone or the following Brion zone and so forth. And in principle, we also have to take into account the momentum of the photoelectron, because that in principle can also carry a photoelectron momentum. Now for low photon energies in the VUV regime, say 20 to 100 electron volts, this can be neglected. This is less than 1% of the typical Brion zone extension. As you go to higher photon energies, say in the order of a few thousand electron volts, that's called hard X-ray photoelectron spectroscopy, or HAXPES. You have to take this into account. It's no longer negligible, but it's just a constant that can be easily taken into account. And the other thing is this reciprocal lattice vector, and that's very neat, because in principle, you can map out several Brion zones here, and this can be done. And I show you as an example the Fermi surface that can be mapped out for the two-dimensional electron system at the interface of LAO-STO, measured here at different Brion zones. This is the original Brion zone where you have zero momentum. So this is 0ky and 0kx. But as you go to higher momenta, you see that the signal repeats itself because of this periodicity in reciprocal space. That's a very nice representation that reciprocal space is reality. It's not just a mathematical concept. You can really see it in an experiment. One caveat at this point here. When I say we have these direct transitions, we have to take into account something like a Debye-Waller factor, something that you also know from X-ray diffraction. When you have a finite temperature, the phonons in your system will, by their very existence, destroy the periodicity of your crystal structure, and transfer spectral weight from your Bragg peaks to incoherent scattering between the Bragg peaks. And a similar thing happens also in photoemission. If the temperature is not low enough, you may smear out all of your momentum information. And this is why very often when you go to X-ray photoemission, nobody talks about momentum conservation anymore. It's always restricted to low photon energies. Because there the Debye-Waller factor, which scales basically with a photon momentum, is not as important. You can beat the Debye-Waller factor by going to very, very low temperatures, so it increases the efforts that you have to put into your experiment. But just to give you an order of magnitude, as soon as your photon energy goes into the kilo electron volt regime, it becomes difficult to maintain momentum resolution. But it's not completely impossible, and we have done recently experiments at very high photon energies where you still see some some K-space information, but I will not address it here, and that's really under very special conditions. Okay, so we have the first step. We had the excitation in the volume. Now the electrons travel towards the surface. And as I mentioned before, the photoelectron will experience, or some of them will experience, inelastic scattering events with other electrons, giving rise to interband transition, excitation of electron hole pairs, and in particular plasmons, so to coherent oscillations of the entire electron system, and they may also generate phonons, and by that lose typical phonon energy. And as a consequence of that, you will have a lot of photoelectrons that have lost their energy and will appear at lower energy, at lower kinetic energy, and give rise to a background of secondary electrons. And that's shown here. Take, for example, this red spectrum here. This would be, for example, a core level spectrum. If we didn't have these inelastic processes, if we are still with this step 1 here, we have an excitation into this final state energy. And now the electrons start propagating from the site of the excitation towards the surface. Some of them lose some energy and will appear here at lower energies, and then they give rise to this inelastic background. And that's what you often see, that behind such a line or behind a spectrum, you have an increase of intensity, which is relatively structureless, as a background that you have to take into account when you want to do any quantitative analysis of intensities. For example, you have to be aware that some of your intensity here is due to the secondaries and it's not intrinsic spectral information. A second consequence of this is that the photoelectrons, the actual ones, still carrying the original energy information, will have only a certain mean free path. I addressed this before, and this gives rise to this inelastic mean free path that we had been discussed. This is this mean free path as function of photon energy, this universal curve that restricts our probing depth to about 3 times the mean free path here from the surface. And finally, and that is important then if you want to do momentum dependence of your photoelectron distribution, if you want to map out band structures, you have to take into account what happens when the electron transits through the surface. Parallel to the surface, we still maintain periodic symmetries. You have a certain crystalline order here in your sample, and trivially, the vacuum has the same order. If you go by a certain lattice constant, nothing changes in the vacuum, and therefore K parallel, the momentum of the the component of the momentum of the photoelectron parallel to the surface is conserved and does not change as the electron goes through the surface. However, the vertical compound K perpendicular, that changes due to electron diffraction at the surface. And that can be understood very easily as the electron goes from somewhere in the interior to the outside here. You see that it changes kinetic energy, because here our energy reference is the bottom of our band. Here it is the vacuum level. And so the momentum perpendicular changes, or in terms of band structure, this is the band structure as function of K perpendicular at a given value of K parallel, which is conserved, which may have this structure here. I excite my electron to this state here. It has a certain energy and a certain small K perp. And then it goes to the surface and then turns into a free electron wave. But in a free electron wave has a parabolic dispersion. We keep the energy here. Energy doesn't change as we go to the total energy doesn't change. The kinetic energy changes, but not the total energy as we go through the surface. It has now this energy at this particular K perp, capital K perp, in the vacuum, and you see that capital K perp does not have to be the same as small K perpendicular. But what we measure, what we measure at our detector is this value of K perp, capital K perp. So how can we get information about small K perp from this? Well, there are 2 ways. Either you know what the band structure here at these photoelectron final states is, and that's typically not the case. Or you assume that way above the Fermi level, way above the vacuum energy, the electrons do not experience the crystalline potential anymore so strongly, and you can replace the true band structure by an approximate free electron parabola, which, however, has a bottom different from the vacuum case, namely here somewhere where you have the bottom of your valence band. It's like assuming that rather than a periodic potential here, you have just a simple potential step from the interior to the vacuum, and the step height is often called the inner potential. And now I have a parabola here, I have a parabola there. The zero here is offset by just this inner potential, and then I have a clear analytic relationship between capital K perp and small k perp. And this is what I measure. V naught, that's the bottom of the band here. I would know roughly from band calculations, and from that I can calculate my small k perp. There are more refined solutions to this problem, how to get this small k perp, but this is a pragmatic one that very often works very well. Okay, and with this we have all the ingredients that we need to do band structure mapping. We measure all these blue properties here, the kinetic energy of the photoelectrons, the momentum that we have in the vacuum, the escape angle of my photoelectron relative to the surface normal. And from that, I can then calculate the binding energy, if I know the work function, the parallel momentum, which is conserved here, and the perpendicular momentum by the method that I just described. And once you have that, then you can map out a band structure. And this is, for example, a band structure including a Fermi surface that we have measured for a particular. In this case, it was an adsorbate system. This was gold on germanium. Okay. But what I have done in this description here is assuming that the electrons in my solid are completely independent of each other, so that I can work with a one electron band structure picture. And that, of course, is a strong approximation. In general, and in particular in our transition metal oxides, very often this is no longer the case, and I have to think about many body effects, and I need a many body description of my photoemission process. And this is what I want to do next. Let's think of our system here. We have electrons in our solid. They interact via, for example, Coulomb interaction, maybe screened Coulomb interaction. I have an n particle system here. And if I do photoemission, I think of it now as a sudden removal of one electron from my n particle system. So I come with my photon here, take out an electron, and what I'm left with is this situation here where there is an electron missing. Now it is obvious that this cannot, what I have reached here, is certainly not the ground state of the n-1 particle system, because if the electrons repel each other, they would now try to fill this hole here, this void, in order to minimize their energy. So they're frozen in some high energy state. However, the state that we have reached here is not necessarily an eigenstate of the system. It is just some excited state. And now the question is, how can we break this down into eigenstates? Certainly, our photoelectron knows about the excitation energy of the state here, because the total energy has to remain reserved. And so the photoelectron kinetic energy contains information about the excitation state of the remaining n-1 electrons. And we can treat this again with Fermi's golden rule, but now we have to use n particle states rather than just one particle Bloch states. So my photoemission intensity as a function of momentum and photoelectron energy epsilon, again, is written here as a matrix element squared. I have an initial state. This is simply just the ground state, the n electron ground state of our system, all n electrons sitting in their ground state. And I have a transition matrix element, which is this A dot P term that we had before, but now applied to all my n electrons in the system. And this can be written in second quantization as an excitation of an electron in state I to an electron in state F with the probability that is given by one particle matrix element that contains, again, the matrix, the momentum conservation. And then I go into a final state. And now we have to be very careful what this final state is. Let me break down this in little steps for you. This final state, again, it's an n particle state. It has one photoelectron sitting in the vacuum. That's what we find at our detector. We have a remaining system here in n minus of n minus 1 electrons, which is sitting in some state, excited state that I label here with a generalized quantum number S. Yeah, so we have an n particle states consisting of n minus 1 electrons in the solid and a free photoelectron with momentum kf and energy epsilon. And of course, we have again momentum energy conservation. We start out with the ground state energy, put in a photon energy, and end up with an excited state that is above, is increased by the original ground state energy by just the photon energy package. And the trick now is to decompose this final state, this n particle final state, in a sensible manner. And that's called the sudden approximation. What I do now is the following. This final state, in principle, is a state in which the photoelectron can still be entangled with my remaining n minus 1 electrons. This is misprint here. This should be an S. And I factorize this out. I forget about this entanglement. The picture that I have is I take my photoelectron out immediately. The system has no time to relax. The entanglement has no way to do anything about this. I take out my electron immediately. So I have a creation operator where I put an electron into the state Kf, the final state Kf at my detector, and I have a remaining state n-1 of the n-1 system, which is the nth eigenstate of the remaining n-1 electron system. And I have to sum up over all such final states that can be reached by this process. There may not be a single one, there may be more than just one. Yeah, but the picture again, sudden approximation means the photoelectron decouples from the remaining system immediately after the photoexcitation before any relaxation can set in. And if you assume this and you plug this into this Fermi golden rule expression and you do a little bit of algebra, which is takes a few steps that are non-trivial, you come up with this expression here, where you have a matrix element between the ground state. You destroy 1 electrons with momentum k in the ground state, and then you map this onto the S eigenstate of the n-1 particle system. With some energy conservation again, and now the final state energy is decomposed into the kinetic energy of our photoelectron and the energy of the remaining n-1 state. And this expression that comes out should be familiar to the many body theorists among you. This is nothing else but the single particle spectral function, which is basically the imaginary part of the Green's function, the single particle Green's function multiplied with the Fermi-Dirac function, because you can, of course, only excite electrons that have been in the system before. And that's the very strength of this expression or of this picture. What we measure here in the many-body picture of photoemission is a response function that is one of the core properties in many-body theory. And so that gives you a lot of information that you can directly compare to theory calculations. Okay, so this wraps up the theory part. So again, what we measure here in terms of electronic structure is not just in a one particle picture, a band structure, Fermi surfaces, but we can really address also the spectral function, self energies, and all these many body things that are relevant for many transition metal compounds. There's A few things that are particular about spectroscopy of photoelectron of transition metal oxides, and this concerns high probing depth and high photon energy, and this is covered here. This is the universal curve that I have shown you before. These straight lines are actually calculated mean free paths for a range of transition metal oxides. And you can see, again, this is very surface sensitive, but in oxides, you very often have a problem with surface sensitivity. One of them is that we want to address interfaces, and they are by definition not at the surface. So we want to get deeper into the material. And very often oxide surfaces are different from the volume. So if you do a surface sensitive spectroscopy, you get information about the surface, which may be nice if you want to study surface chemistry. But if you really want to address questions that are relevant for the volume, you have a problem. So how can we understand this? And one point here, of course, is the ionic nature in oxides. If you have a material that is composed of ions, you have to think very carefully about the distribution of the charges in this ionic compound when you terminate a crystal, when you create a surface. And you can classify the surfaces in different types of structures, categories. You can have a surface where you have an electrically neutral surface, so the charges of all the ions add up to 0, and where you have no dipole moment at the surface. You have surfaces where the surface is charged. For example, here you have all the negatively charged ions on the first layer, and then the positively ones on the next one. But you don't have an overall dipole moment. And here you have a charged surface and a finite dipole moment. These have been categorized by Tasca, and there are nice review articles by Claudine Noguera on that. And this leads to surface reconstructions and surface changes with respect to the volume. And this is due to the polarization catastrophe that most of you will know from the LaOSTO happening at the surface, at the interface of lanthanum aluminate and strontium titanate. But of course, it also happens on the surface of such an ionic compound. If you add up if you look at the charge distribution here in such a type 3 surface and look at the electrical fields and you add them up to an electrostatic potential, you find that this is divergent as your sample becomes thicker and thicker, and that's of course energetically not unfavorable, and so the system will relax in some way, and it will either lead to atomic or ionic or electronic surface reconstructions, and then the surface will be very different from the volume. Here's one example where I would like to discuss this briefly. This is magnetite again, which is a system with wherever you cut a surface into, you always have a type 3 polar surface. And as a consequence of that, you get all kinds of different metastable surface reconstructions. This is a SDM study that we have done a while ago on such surfaces, and you find all kinds of different reconstructions. It's very weird with large periodicities, which simply result from the fact that the system wants to minimize its electrostatic energy with respect to this polar catastrophe. If then you try to do photo emission on this, you find that depending on what kind of surface you have, you get very different spectra. Overall, they are similar. You have an oxygen 2p type main valence band, and then you have here near the Fermi level some spectral weight of variable intensity, which is due to the iron 3D electrons sitting in there. But as you can see, this is taken with helium-1 radiation, which is extremely surface-sensitive spectroscopy. You find very different details here as you look in, especially close to the Fermi level, because of the different surface reconstructions due to this big problem. Now, and the way out is to go away from these small mean free paths by going to higher and higher photon energies. As we go to the right here in this universal curve, you see that the mean free path is increasing as we go to higher energies, but higher photoelectron energies means I need higher photon energy to get them to this high kinetic energy. And if we do this and go to even kilovolts, this is called hard X-ray photon emission, you can get probing depths of the order of up to 100 angstroms and beyond, which is in certain ways still maybe surface sensitive, but no longer on the atomic scale. And that's important here. The price you pay is that at the same time, the cross sections, this is the matrix element here again, between initial and final states, is strongly going down by orders of magnitude as you go to high photon energies. And of course that costs you intensity. So the price you pay is for the deeper probing depth is a loss of signal, and you have to counteract this by having enough photons to begin with, and that's why these kinds of experiments can only be done on a synchrotron radiation source. Okay, let's apply this here to magnetite. This is the same surfaces that we just looked at here with helium-1, now at 700 electron volts. It's not hard X-ray, it's still soft X-ray, but it's already much higher at probing depth. And you can see that the spectra look much more similar now, and especially here close to the Fermi level, there's much more similarity than you have here at these low surface photon energies, surface sensitive photon energies. And therefore, we have here a much better probing depth. That allows you then to also look at fine phenomena on a finer energy scale. For example, here in magnetite, there is this famous Fauvet transition at about 120 Kelvin, where you change from a nearly metallic to an insulating behavior. And that can be resolved then as you go very in very small temperature steps through this transition, and then you can see small changes here in the onset of where the spectra starts because of a small change in the gap. That's only be possible if you go to these high energies. You can also do depth profiling once you have enough depth information, and here I will motivate this with this example of a spin transistor, which depends on ferromagnetic electrodes. And here you have a transfer channel, which typically would be a semiconducting material. So you need a semiconductor, and you need a ferromagnetic electrode, which has to deliver a current of 100% spin polarization. So you ideally want to have a semi-metallic ferromagnet, and magnetite again is as a compound for this, and then you put this onto some semiconductor, and then you hope you get a nice interface. And for example, we have done this. We have grown magnetite on gallium arsenide because that is an interface where you would think that this could match as far as lattice constants are concerned. But of course, you run into the problem that here you have an oxide, you create an oxide, here you have a sensitive semiconductor, and what happens when you start oxidizing the iron here to achieve this magnetite film to the gallium arsenide? What does the interface look like? And then you look again at the core levels of the iron and magnetite. We had studied this before, and you know now that we have certain fingerprints for the valency of the iron in there, and that we can then do by looking at such a film. And then what we change is the probing depth, and we do this by changing the escape angle of the photoelectrons. If we look in the vertical direction, we can exhaust the full probing depth. If we turn now the escape angle detection to a grazing situation, the electrons will come from a much thinner range, so we have decreased the probing depth, but we can also change the photon energy to increase or decrease the probing depth, and by that then do depth profiling. And you can see here as we go from a surface sensitive to an interface sensitive. So here we increase the probing depth from surface sensitive to looking deeper into the magnetite film to see also the interface. You can see characteristic changes here in our spectra, which tell us that we have a mixture here of different valencies, as you would expect in magnetite, but this mixture changes in relative proportions. At the interface, we see mostly divalent and metallic iron. Divalent because we see this characteristic charge transfer centroid. The green spectrum is the one with the highest interface sensitivity. And here you have a peak that is clearly not from an oxide, from oxidized iron, it's metallic iron. But as you go towards the surface, everything looks a little bit more like magnetite. And you can also look on the other side. You can then probe the core levels from the gallium arsenide. And again, you can now change the surface and interface, now in this case, the bulk and the interface sensitivity. And you find as you probe more and more the interface, you get this satellite here in this is the arsenic 2p spectrum, and that's a fingerprint of oxidized arsenic. So apparently at the interface, the arsenic gets oxidized, and at the end, you get a picture at which the interface, where at the interface, oxygen penetrates from the magnetite into the gallium arsenide, so it oxidizes gallium and arsenic, but then deoxidizes the iron, so that you are left with iron OX and metallic iron. And so you have a lot of chemistry going on in the interface that would impede the actual functionality in such a transistor. And this is confirmed here by transmission electron microscopy. Here you have the gallium arsenide, here you have the magnetite, and here we have a range of basically metallic iron here. So it doesn't get oxidized, or the oxide that you try to pump in here gets absorbed here in the gallium arsenide. And you can see this also when you do the chemical analysis by stem yields as you go through this interface region here. So gallium arsenide is not a good material for that. We found then that the zinc oxide is a nicer material for this, but I don't have the time to discuss this in any more detail. Jochen, how much more time do I have now?
About -2 minutes.
Okay, maybe I will then skip this here at this point and do this resonant photovision part tomorrow. And go towards my end here. Let's go here. And take this here as my resume for today. Thank you.
Thank you, Ralph, for this very, very clear presentation. I think you've deserved an applause. The chat window is still empty. I think it was very clear what you told us. If we have, yeah, here is a remark. Thank you for the very nice presentation. How can you distinct a core potential drop and the inelastic scattering in a spectrum background?
How can you distinguish that? That is a good question. By long years of experience would be the honest answer. Well, when you look at a spectrum, let's see if I have a clear spectrum here. Maybe I should go here. When you have a situation like this here, for example, you have this blue situation. It's not obvious which of that is due to the spectrum and to the intrinsic spectrum. What is due to the integral? Now we have a clear picture what's going on here. This is a convolution of the intrinsic spectrum with the so-called loss function. If you have an electron, if you do electron energy loss spectroscopy with a primary electron that has a defined kinetic energy, you get as a response function the loss function, and what we see here is just the convolution of the actual spectrum with this loss function. You can try to deconvolve this out of our spectrum by assuming that your loss function is basically just a step function. And then there is an iterative procedure. This is called Shirley background correction that would do this automatically for you, but it relies on a certain assumption on the shape of the loss function. What you can also do is you can measure the loss function, which is an extra experiment. That's a lot of effort to do. But there are some certain ways you can parameterize these loss functions. This has all been worked out by Tugard, who has done this extremely precise, especially for silicon compounds, because it's an obvious demand in the characterization of semiconductor samples. But in principle, when you see an intense line, intense core level, very often it is relatively obvious what of the spectrum is due to the background and what is due to the intrinsic spectra. But of course, there are situations where this is not so obvious, and then there is a certain degree of arbitrariness in this.
Good. Thank you for this answer, Ralph. Because there will be much more time tomorrow for asking questions, let me wrap up the session for today. Thank you again, Ralph, for this presentation. And I wish all of you a great afternoon or a great day, depending where you are. Do something wonderful with it. Bye-bye.
Okay, bye-bye.